So we've seen the way that we interpret log transformations. It gives us this percentage change interpretation when we're looking at the slope. So what are going to be our options for data transformations? So actually we're going to have 4 options that I can see here. You can either transform the y variable, the x variable, or the y and the x variable. So these are going to be the 4 models that we can look at. Whenever we've got some data, we want to try and present this data out in a linear fashion. That's the nature of what we're going to do. We do that because we know how to work with the equation of a line. Okay, so our primary idea here is we want to fit a trend line to the data. We want to transform the data so that it looks linear, or at least as linear as we can make it, and then we're going to fit our trend line. Okay, so we've got these options here. So the important thing for us to note is how do we interpret the slope coefficient in these. So remember I said we're largely not going to be that interested in the intercept values, but we are going to be interested in the slope values. Okay, so let's start with the first one. I'm going to call this the linear model, and that's easy. Okay, so we don't have any transformation on the data. We just know that the slope is beta, and we can say a 1 unit change in x leads to, on average, a beta units change in y. So it's important in this sort of regression model language to use the term on average. Okay, so a 1 unit change in the variable on average. Remember, our model is not going to be perfect. It's just describing the overall trend in the data. So we always need to put in this qualifier on average. Okay, so that one's easy. That one's straightforward. First, the next one we might not have seen before. So this is when we're going to have the log y transformation. So what are we going to have here? So once I put the log y transformation on here, you can see that the way that these steps drop out, I say that, okay, what is the slope coefficient? The slope is rise over run. Okay, what is our rise? Our rise is the change in log y. What is our change in x? Well, we're going to say a 1 unit change. So the change in log y is equal to beta. Now, what do we know about log changes? We know that if we multiply them by 100, we get a percentage change. So once we put the log y transformation on our data, we interpret our slope as saying if we take the beta coefficient and multiply it by 100, a 1 unit change in x gives us a beta times 100% change in y. So we've snuck in that percent change formula. Now the next one is then when we put the log transformation on the x variable. So if we flow through this again, you can see rise over run. We're going to get, the description is going to be the change in y. On the bottom we're going to have the change in log x. And again, we know that if we multiply that change by 100, it's going to give us a percentage change. So a 1% change. And when we multiply that by 100, it means that if we divide our beta coefficient by 100, we get our interpretation for y. So we're going to say when we have a log x transformation, we're going to say a 1% change in the x variable. So remember, that makes sense because we've put the log change on the x. So it's a 1% change in the x variable results on average in a beta divided by 100 unit change in the y. So again, the y is still in the original units of measurement. It's just the x variable that's in the log scale. And then of course our final option in this setup is the log-log transformation. So if we look at that, that's the one that we've seen already. So it just means that a 1% change in x leads to, on average, a beta percent change in y. So you can see that we've got these options. So how are we going to interpret these? So our no transformation model, say our result was y is equal to alpha plus 650x. So this would be our model. Our model looks approximately linear on the original scale of the data. Our slope coefficient, our generic statement of 1 unit change on average, what will we say if we specifically have a value of 6,500? It's a 1 centimeter increase in fish length, leads to an increase in egg production of 6,500 eggs on average. Okay, if I had the log y transformation on my data, so I have some result that looks like this. Log y is equal to alpha plus 0.095x. What would we say? We'd say a 1 unit increase in x. So what are the units of measurement of x? They are centimeters. So a 1 centimeter increase in fish length on average leads to a 9.5% increase in egg production. So my plot is going to look approximately linear on a log y normal scale x plot, and my interpretation of the beta of 0.095 is that 9.5% increase on average in egg production with a 1 centimeter increase in fish length. The next one that we have is the log transformation on the x. So I've decided that my data looks linear when I put the log transformation on the x. Say I have my notation here. I don't know, again, I've got another typo there. That should be y, not log y. Alpha plus 32,000. What would we say? We would divide through. Okay, we have to divide through that coefficient. That's going to give us our increase in egg production. So 1% change in fish length, you take the beta coefficient, you divide through by 100, and that's your increase in y. So it's the percentage change notation is applying to the x variable. And our last one, for whatever reason I've decided, well, not for whatever reason, for the reason that the plot that looked most linear was the plot that had a log transformation on y and a log transformation on x. I set these guys up. I'm going to have this 1% change in fish length leads to a 4.8% increase in egg production. So my scale, I'm going to have log on the vertical and log on the horizontal. If beta is equal to 4.8, 1% increase in fish length leads to 4.8% increase in egg production. So again, some fairly heavy concepts to take in there, and that's an opportune time for you to have a break.